Hello, we are undergraduate students from the University of Toronto Sports Analytics Student Group, and will be presenting a holistic player evaluation model with a metric we created called RIPP, which is an acronym for Region-Based Isolated Player Performance. An example of a player in the NHL that is valued much more by analytics than standard statistics like goals and assists is Craig Smith. If you look at his box score, you'd see unimpressive numbers like a career 0.5 points per game, but advanced metrics like WAR say he's a very high-level player in the league. We hope to be able to identify the best players in the women's game too.
Right, so we have two primary goals for this project. The first being to use play-by-play data to successfully evaluate individual player actions. For this project, we will use play-by-play data provided by Stathletes. And with this data, we hope to develop a system capable of isolating individual player performance. Next slide. We will draw inspiration from research in other sports which have successfully used state-based or region-based models to identify standout players and formulate our own metric called RIPP, Region-Based Isolated Player Performance. Next slide. At the abstract level, the RIPP metric consists of two mathematical models. The first model is an expected goals model, which assigns a value to every location on the ice based on the probability of scoring from that location. And the second model determines the value of a play as a difference between the value at the end location of the play and the value at the start location of the play. So in the diagram below, if we have a pass which goes from location A to location B, the value assigned to the player who makes that pass is the value at location B, subtract the value at location A.
To give a concrete example with some concrete numbers, we show this example. So here a player has made a dump from location 1 to location 2. Since the value at location 2 is 0.64 and the value at location 1 is 0.26, we assign this player a RIPP of 0.38 for this action. The next action, a player has carried the puck from location 2 to location 3, which has a value of 0.59. Here the RIPP is negative 0.05. And so we continue until we get to location 5, which has an expected goals value of 0.74. When a player shoots from this location and scores, that gives an end value of 1 for a goal. And so the RIPP for that player is 0.26. So now that we've explained theoretically the framework that we're using, we're going to develop a proof of concept using the data provided for the Big Data Cup. There are two things we need to define in our proof of concept. First of all, what are the states and the value for each state? And second of all, we need to define the start and end states for each action type. Next slide, please, Aaron. And another one, please.
In hockey, possession is estimated using a metric called expected goals, where logistic regression models are fed contextual data like shot distance, shot angle, time of shot, and number of skaters in order to determine the value or danger of a scoring chance. On the right, we can see Craig Smith's expected goal, and the number of shots he generates from very close to the net is the reason why the analytics community values him so highly. In our research, we discovered that nearly all hockey expected goal models value shot distance and shot angle as two of the most important pieces of contextual information. The model by Evolving Wild lists shot distance as being by far the most important variable, with shot angle being the third most important. In our work, we consider the angle as being the visible angle, which is the portion of the net that the shooter could see from wherever it is they're shooting from. We use the Pythagorean theorem to calculate the distance to both the first and second post, and knowing that the width of the net is 6 feet, we applied the cosine law to calculate the visible angle. Knowing both the visible angle as well as the distance to the net, we inputted both these pieces of information to a generalized linear model in our studios, which gave us the value of a scoring chance from anywhere in the offensive zone. We note that the model assigns the highest expected goal values to shots directly in front of the net, with the expected goals decreasing the further away you go. The model is generally in line with our intuition. However, shots from close range are somewhat overrated, and shots from the tops of the circles and high slot is somewhat underrated by our model. This is extremely common in public expected goal models, which rely heavily on shot distance and shot angle as their key pieces of information.
Here you can see a chart of all the different event types that we used, along with how we valued them in the play-by-play data provided. Our model's foundation is based on how much the probability of scoring a goal changes from one location to the other location. This is why you can see for a play, we have made the RIPP value worth the difference between the XG of the pass's end and start location. On the other hand, if the pass was incomplete, the RIPP would be the difference between the opponent XG at the end location of the incomplete pass and the XG of where the pass was from. The remaining event types we used operate under similar start state to end state logic.
So now that we've presented our implementation, we're going to walk you through some results. First of all, we're interested to know whether our metric RIPP is capturing the value that a player is adding to their team effectively. One way we do this is by plotting the player's average RIPP per game against their average goal scored per game. We can see here that the most prolific scorers in our data also tend to have pretty high RIPP per game values, which makes sense as they're likely key cogs in their team's offenses. However, we can also see that a player can achieve pretty high RIPP per game even without scoring a lot of goals. In fact, some players with 0 goals have pretty high RIPP per game. On the next slide, we show us a table of the top 10 players according to their RIPP per game, with at least 5 matches in our data. It's nice to see that the top player here, Michaela Grant-Mentis, also represents Toronto and was the MVP of the league in that season. And so this is another indication that RIPP is really capturing the value of the player well.
Our RIPP calculation demonstrates the value added by a player in all facets of the game, which allows coaches to determine their most valuable players and also to find potential weaknesses of the player's game. From Marie-Philippe Poulin's chart, we know that she adds the majority of her value with her goal scoring, her passing, and her puck recoveries. However, Poulin misses the net and fails to complete passes more than the average player, and a coach may use this information to maximize Poulin's talents, such as playing her with strong playmakers so she can best use her goal scoring and shooting abilities.
Lastly, we'd like to discuss some limitations of our current approach and some possible next steps for future work. I think the biggest flaw of our current implementation is that we're not well valuing off-puck actions and defensive actions. One promising avenue to address this is to use tracking data, which would ideally allow us to assign values to all of a player's actions, both on and off the puck. Thanks to providers like Stathletes, tracking data is becoming more readily available for the analytics community, and especially in women's hockey. The second limitation is that we're using an expected goals model as the state value for all the states in our framework. However, very often during a game, you don't really care about the immediate probability of scoring from a position. What you care about is the probability of scoring in that possession or in the next few seconds. For this reason, a better approach might be to use a time interval from a given play and model the probability of scoring within that interval. This is a method that was proposed by a paper called V-ICE from the Big Data Cup a few years ago. Lastly, we want our work to really drive forward analytics in women's hockey. We hope to release our code as an open source R package so that other analysts can use RIPP in their work and expand upon what we've done. So lastly, we want to thank Stathletes for hosting the Big Data Cup and the reviewers for their insightful comments. And we look forward to answering your questions at the live panel. Thank you.